So in the previous video we have watched that if we have a data plotted on a graph x and y, then we can find the equation of the line between them, which minimizes the error between the actual and the predicted points, which comes out as a equation of a line y equal to mx plus c. And here we had to find this slope term m and this intercept term c. But now if y is dependent on only one x, then we can draw a line. But what if y is dependent on multiple x's like x1, x2, x3? I mean, like in our previous video we saw that height is dependent only on weight. But does this occur in real life scenario? There are many more factors. Let's change our example to the car example which we took. Now price of a car will be dependent on mileage plus distance it has traveled so far plus years it has been used plus maybe brand like Benz, Rolls Royce. These are high costly cars. So there are many factors or features which determine the price of a car. Simply we can tell that y is dependent on many x. Now how to predict y when we have these many x? We know that for one x and one y we get a straight line in a 2D data. But what if there are more? If we have x1 and x2, which will determine the value of y, then how will our graph look? Just a minute. Now assume this is for 2D data x, y. But since we have one more variable, we get another z coordinate also. It becomes a 3D data. And here if we assume this as x1, this as x2, here we will have y. And the equation of a line will slowly convert into an equation of a plane like this. It lies somewhere here along this axis. But if we have more than 2x, x1, x2, x3, x4, like this we have n dimensions, then we can't even draw the graph. We can't comprehend these many dimensional data. But we can surely predict value of y based on these. How? Let's have a quick one more look at the derivation which we did. We know that y is equals to mx plus c and our loss function is y minus y pred. Y pred is this mx minus c whole square sigma, right? Now what do? We differentiate L with respect to m, put it 0. Let's do it. So if we differentiate this entire term with respect to m, then this 2 will come out. We have looked this in detail in the previous video. Sigma will be as it is, 2 will jump out. This entire term will be written as it is, y minus mx minus c into this differentiation of this inside term. Y is a constant, 0 minus m into x with respect to m will become minus x and c is a constant, again 0. This is equal to 0. Now if we take this minus and 2 to the other side, then there is going to be no change. We have sigma, 2 cancelled out, minus cancelled out, x goes inside. We have xy minus mx square minus cx equal to 0. Now we can distribute the sigma on these terms. So we'll get sigma xy minus m is a constant, m will come out, m sigma x square minus c is a constant, c sigma x equal to 0. Now let this be our first term. Now let's also do dl by dc equal to 0. dl by dc equal to 0. So what do we get? Let's quickly copy this. Now dl by dc equal to 0. Again the same, sigma will be staying, 2 will come out, 2 times y minus mx minus c into. Now here this entire term is 0 as it is constant. This is also constant with respect to c. 0 0 minus 1 equal to 0. Now this minus we can send other side, 2 we can send other side. So we will be left with sigma into this term, and sigma can be distributed. So sigma y minus m is a constant, it will come out, m sigma x minus c is a constant, c sigma 1 equal to 0. Now let this be the second equation. Let's copy the first equation. Now these are the two equations which we have. Let's rearrange them a bit. So we have sigma y, 1 implies sigma y equal to, if we send these both to the other term, we have m sigma x plus c sigma 1, and second implies, if we send these both to the other side, sigma xy equal to m sigma x square plus c sigma x, right? Let's copy them to the other page. Let's just interchange LHS and RHS. So we will get C sigma 1 plus M sigma x equal to sigma y, C sigma x plus M sigma x square equal to sigma xy. Now if we take close look at these both equations, can we write them in matrices form? Yes. We can write them as matrix sigma 1, sigma x, sigma x, sigma x square into this C and M is another matrix is equal to sigma y, sigma xy. You might ask, what's the use of writing like this? Well, wait. Now let's take a capital X which will represent a matrix or data points x values, but we will pad it with 1 in the first. 1, 1, 1, and how many endpoints are there? Those many. Then this will be x1, x2, x3. This is our capital X and capital Y. y1, y2, y3. This is our x and y. Now what will be our x transpose? Just interchange the rows and columns. 1, 1, 1, x1, x2, x3, right? Now what will be x transpose x? 1, 1, 1, x1, x2, x3. This is x transpose, and x is 1, 1, 1, x1, x2, x3. Let's multiply them. Then we are gonna get x transpose x equal to 1, 1, 1 into 1, 1, 1, and they are n points. So we can just write it as sigma 1, and this 1 into x1, 1 into x2, 1 into x3 till n point. So we can write it as just sigma x. Same goes x1 into 1, x2 into 1, x3 into 1. Sigma x, x1 into x1, x2 into x2, x3 into x3. So we can write it as sigma x square, right? Now, don't you see this is somewhat similar to this matrix? Let's look at another term, x transpose y, which is this term into this y. So what do we have? 1 into y1, 1 into y2, 1 into y3. Can we just say sigma y? Yep. x1, y1, x2, y2, x3, y3. Can we tell sigma xy? Yep. Now, as you can see, this is beta and this is x transpose y. So what do we have the final equation as? X transpose x into beta equal to x transpose y. Now you may ask, what's so great in this? Wait and see. So we have this equation, x transpose x into beta equal to x transpose y. The beauty in this equation is we can calculate the required values of slope and intercept in an instant without doing the long differentiation which we did. Why? Simply just beta is equals to, now as you can see here, this x transpose x is a square matrix, so it is always invertible. So inverse of this always exists, and we can write x transpose x inverse x transpose y. So beta equal to x transpose x inverse x transpose y. And simply we know that x transpose x is nothing but sigma 1, sigma x, sigma x, sigma x square, and we also know that x transpose y is sigma y, sigma xy. We can instantly calculate these and put it into our equation to get the values of beta. No need to do any mind-blowing differentiation for this. And also there is one more advantage. Now assume our x, which is our input data points, are instead of being one dimension, they are n dimensional. But remember, the first column will always be padded with 1. 1, 1, 1, 1 goes on. x1, 1. Here the superscript is not power, it is the feature number. Let's call this as feature 1. This is feature 2, first data point. Feature 3, first data point. Feature 4, first data point. Like this it goes on till we have D features and this first data point. And this is X. Feature 1, second data point, X. Feature 2, second data point, and this goes on till we have XD features. and 2 data points, and this finally we will stop at x dth feature nth point, right? Now this is our x. If you have n data points of data with d features, you can find this beta values using this formula in an instant. Just this, and we also know what is x transpose. Just interchange the rows and columns. We will get x transpose x, take its inverse, multiply it with x transpose y, we will get beta. Our work is done. But now one more important thing. Let's find the dimensions of beta. We know that x has dimensions of n data points into d plus 1 feature. Why? Because if you have d features, we are padding the first column with all ones. We have x as n into d plus 1. X transpose is going to be d plus 1 times n, and we know that y has an order of only one feature but n rows, so it will be n into 1. Now what are the dimensions of x transpose x? X transpose x, this is gonna be x transpose is d plus 1 into n, and x is n into d plus 1. So as you know, m into n, n into p, the number of columns in the first matrix should be equal to number of rows in the second matrix. Resulting matrix is going to be order of m cross p. Therefore it is d plus 1 cross d plus 1. So we can tell that x transpose x is a order of d plus 1 into d plus 1, right? Now let's look at the dimensions of x transpose y. We know x transpose is d plus 1 into n and y is n into 1. So x transpose y is going to be this n gone, d plus 1 into 1, which is d plus 1 into 1. Finally, we have x transpose x into beta is equal to x transpose y. When we send it to the other side, we have beta equal to x transpose x inverse x transpose y. Now, the order of a square matrix is equal to order of its inverse matrix. So even this is going to be d plus 1 into d plus 1, and x transpose y is going to be d plus 1 into 1. Therefore this d plus 1 d plus 1, and we'll have beta's dimensions as d plus 1 into 1. That is, we have d plus 1 rows and 1 column. And it also makes sense because as you see in our first example of x being 2D data, we had x equal to 1 1 x1 x2 and y equal to y1 y2. Here we have only one feature, and as per this formula, what do we get? We have 2 into 1 plus 1. As you can see, we have two data points, 2 into only one feature which will predict the value of y. So 1 plus 1. And same goes for y. We have two data points into 1. As you can see here, n number of data points into 1. And now what will be the final order of beta? It's gonna be d plus 1 into 1, which is nothing but 1 plus 1, which is 2. And we also know that final beta which we got, it represented C and M. We can also write it as beta naught and beta 1. This first term in beta is the bias term, or we can also call it as intercept term, and this beta 1 is the coefficient. In our model, we will get finally y is equals to beta 1x plus beta naught. And if y depends on n data points, then it's gonna be beta 1 x1 plus beta 2 x2 plus beta 3 x3 dot 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 dot, and lastly beta n xn plus the extra bias term beta naught. That's it. Thank you.